Quantum entanglement. It's gotta be one of the weirdest, most mind-bending ideas in all of physics. But what if the whole spooky part of it isn't real at all? Today, we're diving into a really radical take from an outsider who says, hey, there's a simple, mechanical answer to this cosmic mystery. So yeah, let's get into it.
This right here, this is the big question. What if that spooky action at a distance, the thing that famously freaked out even Albert Einstein, actually has a simple, logical explanation that's been hiding in plain sight this whole time? That's the wild idea we're going to unpack.
All right, but before we can really get into the counterargument, we have to understand what all the fuss is about in the first place. So let's do a quick recap of the mainstream view on this so-called spooky connection. Okay, so picture this. You have two coins, and they're magically linked. You could send one to the other side of the galaxy. The very instant you look at yours and see that it's heads, you know, instantly, faster than light, that the other one is tails. That's basically what's happening with the spin of these entangled particles. And that is what gets it the nickname spooky. How in the world does that second particle know what happened to the first one instantly, across maybe light years of empty space? It seems to just shatter the ultimate speed limit of the universe, the speed of light. So this apparent paradox, this puzzle, has led a lot of physicists to a pretty radical conclusion about how reality itself actually works. And wow, this quote from physicist David Z. Albert really sums it up. The argument, which is based on some groundbreaking math by a guy named John Bell, is that since no local cause and effect explanation seems to work, well, the connection has to be non-local. It's just a fundamental feature of our reality. So let's be clear, non-locality isn't just a placeholder like, oh, we haven't found the thing connecting them yet. No, the theory is saying there is no thing. There's no invisible string, no mediating force, no travel time, just a genuine, instantaneous, magical-seeming influence. The spooky part isn't the mystery, it's the proposed answer. But hold on, what if that entire conclusion is built on a massive leap of faith? What if it's all just a fundamental error in logic? Well, this is where a really powerful counterargument steps into the ring. And there's the counterpoint, laid out in just 3 words. Independent researcher Miles Mathis argues that declaring reality is non-local isn't some great scientific discovery. He says it's an act of pure scientific arrogance. Mathis's argument is basically a 3-punch combo. First, he says the whole conclusion is built on a logical fallacy. Second, he says it completely ignores a huge scientific unknown, the charge field. And third, he claims it's basically deceptive to sell this non-physical idea to the public as being realistic. And this, right here, is the core of his accusation. He's saying that entanglement didn't prove reality is non-local. No, it proved an old assumption was wrong. But instead of going back and fixing that broken assumption, he says the theory was just patched up with what he calls force at a distance magic. Okay, so if it's not magic, what is it? If there's a mechanical, nuts and bolts answer, what could it possibly be? Well, the proposed solution is actually surprisingly simple. And get this, the answer actually borrows a conceptual tool from the legend himself, Richard Feynman. To explain some weird particle behaviors, Feynman imagined assigning a tiny clock and a little arrow to every single particle. So Mathis takes this abstract idea and makes it totally physical and concrete. He says the clock isn't some metaphor, it's the particle's actual spin, like a tiny spinning top. And the arrow, that's just the direction it's heading. That's it. And this simple idea, well, it changes everything. Okay, here's where it all clicks. Imagine our 2 entangled particles are born at the exact same moment, but in perfect opposition. So if particle 1's little clock starts at the 12 o'clock position in its spin, particle 2 is created at the exact opposite, the 6 o'clock position. And boom, there it is. If their spin rates are identical, they will always and forever stay in perfect opposition. When one particle's spin hits the 3 o'clock position, the other one is guaranteed to be at 9 o'clock. There's no spooky communication needed. The connection isn't magic, it's memory. It's baked in from the very beginning. Now, this isn't just some technical debate about tiny particles. According to Mathis, the acceptance of non-locality represents a really dangerous turning point for the entire field of physics. That's a pretty provocative statement, right? Mathis is basically arguing that when physics starts to embrace ideas like non-locality, it's abandoning its most fundamental job, to actually explain the physical mechanical universe that we all live in.
And this is where this whole debate becomes a kind of proxy for a much bigger battle, maybe a battle for the soul of science itself. Is the goal to find the physical gears and levers that make the world tick? Or is it enough to just build mathematical models that predict what's going to happen, even if the model itself feels kind of like magic?
So ultimately, this outsider's take on entanglement leaves us with the huge question about the future of science. Is a theory a success just because the math works out and it makes good predictions? Or does it also have to describe a reality that's tangible, mechanical, and in the end, something we can actually understand? What do you think the true goal of physics really is?